Good afternoon, guys. It's a pleasure to be here to share our presentation here with all of you this afternoon. We'll be talking today about managing life cycle of the operating systems in a deterministic way. So, a few things that we'll be talking about today would be the traditional way that we use to manage OS lifecycles as of today, shortcomings of such a traditional approach, how we have approached such a problem, why we're resorting, and the reasons behind approaching the problem differently, and would this be a right approach for you? All right, traditionally we have seen the OS lifecycles are managed today is in a data center environment. The way it works is majority of the machines that are coming into the data center get the IPs allocated to through the DHCP server. And after the DHCP server has the IP allocation done, that's when the machine comes up, the IP is allocated, and it's basically using a PXE-based mechanism to build the host. We'll kind of break down the entire mechanism into pieces and explain where we are making changes with this new approach. So the server in question, this server, is the machine that needs to be built. Assuming that this has been allocated the IP and the machine comes up in the data center environment, it's going to request the IP from the DHCP server. The DHCP server responds back with the IP address for the host, the TFTP server IP address, and the NBP, the network boot program location. The server in concern ends up reaching out next to the TFTP server and requests for the bootloader. The TFTP server provides the bootloader. The location was previously provided by the DHCP server. Now, once it gets the bootloader, it is going to fetch the kernel, and that generally in a data center environment is either provided by the TFTP server or the HTTP server. The server gives back the kernel, and the server that is being built would request for IP from the kernel, from the DHCP server. The DHCP server allocates the IP for the kernel, and then the server fetches the kickstart file, the post-install script, etc., and starts building. What we are proposing here is making changes to this part so that right now what happens is it ends up fetching the kickstart. Kickstart provides the yum repository information. Yum repository, the server then fetches packages from yum repository, tries to resolve it, resolve the dependencies, fetch the entire list of packages, and then start deploying the packages. What happens if, say, you have a site in APAC and, say, the yum repository is located far west, somewhere in Americas or something? In that case, the total round-trip time increases drastically. Imagine resolving all the dependencies for packages, downloading all of these packages, and deploying them onto the host would take enormous amount of time. What we are proposing is changing to this mechanism, which Sudhindra is going to go through. Couple of shortcomings with this approach is one is what happens if the yum repository is located far west. The other one is if there are multiple repositories and you are fetching packages from multiple repositories. In that case, you will have to make sure that these repositories are reachable from the end host. Now, what happens if you do not want, say, a host in DMZ to have access to these repositories? Then you are supposed to plug holes through your proxies to get through, right? The other issue is in a data center environment, there'll be multiple vendors for all kinds of hardware that we have. So in a multi-vendor environment, the number of packages which may be allocated for each vendor would increase. So that also changes the software bill of materials from physical hardware to hardware if they are from different vendors. In that case, we also would want to run compliance across each different physical host from different vendors. This also requires a couple of additional software that you would need in order to manage multiple vendors, right? Say you want to, for example, configure out-of-band. Out-of-band for HP would require different set of tools if you want to configure it through the host itself, through the operating system, versus, say, from Dell or other vendors.
Yeah, so thank you. So yeah, so before we just go through this entire diagram of how we do it, just a quick show of hands, like how many of you do work in different cloud data center environments versus only working with AWS or only working with GCP? If you can just get a quick show of hands. If you do work in multi-cloud setup. So yeah, so I guess that this will be like pretty useful for you. So yeah, so like Pranay did mention that there are quite a few number of issues when you're dealing with hardware types which are of different vendors, each of them with their own different list of drivers, each of them with their own different list of software packages and all of that. It's fine if you only have a couple of these, or maybe you can count them on your hand or something, but once the number goes beyond a certain value, you need a better way to manage or maintain consistency so that when applications do get deployed on them, they know what to expect, and you are certainly sure that each host has the correct version of packages, each has the correct version of packages, and all of that sort of stuff. So, I mean, there are a few solutions, obviously industry-wide solutions. The most popular one, I guess a lot of people would have heard of, is Docker and Docker Compose. That's one way to ensure that every image which is on a particular host, which is running on a particular host, is of the same type. And then the other way is obviously VMs. And the one approach which works for us is the VM one, because there's a lot of, we can easily build complexity on top of those and stuff like that. So just this diagram just gives a brief overview of how this works. So for example, on the left, you see that we have certain configuration files, each for different operating versions, because we offer multiple of them. So for example, Linux has a thing, Windows has a thing, applications might have a thing, databases might have a different image type. All of them get built. We'll talk about the technology later. And then comes the configuration layer. Obviously, here is where you would do all sorts of pre-configuration. You can use a number of tools. There's Chef, Ansible, Puppet. You can run shell scripts if you want to create directories, you want to create users, you want to create permissions, you want to add your monitoring stack, perhaps you want to add your logging stack. All of this before you actually hand it out to an application developer or an application developer team. So when they get hold of the server, this image, they don't have to do anything. It all comes pre-configured with everything. And then once you have these artifacts, so it could be a Windows one, it could be Debian, it could be Ubuntu, it could be Red Hat Linux, whatever it is, and you obviously like make it available to everyone who's using yours. So AWS does it through their AMI marketplace. I'm sure Google has one. So similar, so just an image registry where it's sort of like a one-stop shop for all sorts of images. People can just come, choose what they want, launch an instance with it, and all that sort of stuff. So yeah, so this image registry is used by all our compute clouds to launch instances, to refresh them every time we have like new versions of images. And then obviously by the upgrade workflows which apply security patches if there are new versions of packages which need to be fixed in order to like, I don't know, fix certain CVEs or anything like that. Then yeah, so when during maintenance windows, they automatically get upgraded and all of that. So, I mean, if you can see, we talk a lot about this one particular tool called Packer. How many of you have heard of Packer before? Well, then you're in luck because there's a small refresher on what Packer is, or a small introduction. So Packer is actually an open source tool. It was released in 2013 by HashiCorp. I'm sure everyone's heard of HashiCorp, Vault, Terraform, all of the things which come from them. Packer was actually one of their first software products which was released to the market along with Vagrant. So Packer, what it does is it lets you create identical machine images for multiple OS platforms and for multiple OS types. So what that means is you can create, so having a same config, you can create images for AWS, you can create AMIs for AWS, you can create images for Google Cloud, you can create images for Azure, or you can even create images for your own data center environment, all using just one tool under one repository. And yeah, so prior to Packer, obviously it was very limited. You had to like be tied down to the one platform you were using, and then you had to follow their way of like doing how you would create images for all the instances you would launch under that one platform. And obviously Packer builds all of these for these platforms using just simple commands, and obviously it can be automated as well, which we'll look at. Just a quick one. So Packer just contains 3 main components that everyone should know about. So the first one is the builder. So this is essentially the main workhorse of the Packer software. And what it does, it reads certain configuration you give it, and it builds a virtual machine out of that configuration. The second one is the provisioner. So what it does, once the build is complete, the provisioner would come in. It could be Chef, it could be Ansible, it could be Puppet, it could be simple shell scripts, and they will run whatever you want it to run. They will apply whatever configuration you want it to apply, be it create new directories or install some network tools on it so it's useful for debugging and all that sort of stuff. And then finally, we have post-processor. So these are just stuff which will take this running VM or this running instance, package it in a way which is useful for AWS, so creating an AWS machine image, an AMI, or creating a raw image for something. There are formats like QCOW2 for OpenStack and all of this sort of stuff. So the post-processor just comes in, it creates the image you want it for the cloud you want it for, and then just push it to that cloud. Sorry. Yeah, so the things which we spoke about earlier, the builder. So the builder basically relies on 2 different things. So the first one is template. So the template is basically your config file. You can add whatever you want in it, like how you want the machine to build, where to fetch the ISO from, where to fetch the packages from, and all that sort of stuff. And finally, the data source. So these are like dynamic calls. Again, this is a very HashiCorp concept. I'm sure if you work with Terraform, you would have heard of these 2 things already. But essentially, data source just fetches data from whatever APIs are there in the web to like determine what kind of image to build and all that sort of stuff. So yeah, so we spoke about our approach. So just going a bit more deeper into that. So we built this with a lot of open source technology. We tried to keep it as reproducible as possible if someone else wanted to do this, and we didn't tie it down to a lot of enterprise stuff. So anyone can do this pretty much because all of these technologies are free, free to access, free to implement, free to use. So yeah, so it works really well, especially at a very large scale, considering how big Bloomberg is. It works at a very large scale as well. So we have a set of base of Packer configs. So these are essentially configs for each operating system that we provide. And the different clouds also. So we obviously operate in multiple clouds, multiple environments all around the world. So for each of them, we have a base of configurations. And then the Packer pipeline or the build process, this entire CI/CD thing, will pick up these configs and fetch the images, the ISO medias which are stored in the repositories, and install the operating systems. Then we have various provisioners come and configure this. So yeah, like I already spoke about, it's setting up directories, installing packages, setting up users and groups, setting up the monitoring stack, setting up the logging stack, installing debugging tools, and all of that sort of stuff. And then finally, one of the good things you can do is you can also run integration tests on all of your builds to make sure that everything is set up properly. You can run tests to make sure that all the permissions are configured properly and all of this sort of stuff. And once this entire thing is done, we upload all of these new images along with their checksums and all of this sort of stuff to our central image repositories. And then they can subsequently be promoted to different tiers, so dev, alpha, beta, prod, based on whatever cadence you want to do. So it makes it easy for people to test new patches, new fixes, new versions, and all of that. This entire thing, like I said, works as a workflow in our CI/CD system. So it completely automated. There's no human interference required, honestly. Every few days, there's a new version which is pushed out, and it's refreshed, so our fleet gets refreshed with the latest packages, with the latest fixes, and all of that sort of stuff. Hand it back to Pranay now.
All right. Thank you, Sudhindra. Why are we doing it this way? Primarily because this makes the images portable across physical as well as virtual environments. That helps us to keep the image generation as well as the image deployment consistent across the board. We also use the baseline configuration that we have for each of these platforms. What that does is when we have to port it to a new platform, very minimal number of changes are required, and you can have pretty much the new platform available in literally on a flick of time. From the SRE point of view, this really helps them to ace the entire troubleshooting, since the list of packages and the overall operating system is not different from one physical system or one virtual system to the other. And that also helps us to improve the efficiency across the builds. Like I said, if the repositories are located far west, fetching each of the packets, and generating a new TCP connection, terminating the TCP connection, generating a new one for the next package is going to take humongous amount of time. Since this image is literally the golden state that we take it in, the final state of a physical host is very similar to what state the image is in. That way, not a lot of changes are needed post-deployment of the image on the physical host. Say, for example, if you have a physical host where you have to deploy the operating system and then run chef, run salt, workflows to get it into a usable state, all of that gets obviated. All of that is done right away on the image generation time. That way, if you're building 1,000 hosts, the amount of time you are going to save is exponential. You also don't have to worry about permissioning directories, SRE NEXT permissions, etc. All of that is taken care of during the image generation piece itself. Also, if the image is based out of RAM or physical disk, it does impact, to an extent, the deployment of the image. If it's in RAM, it does take some more amount of time versus on a physical disk. But overall, we have seen about 40% increment in building a machine through the standard mechanism using Kickstart versus deploying the virtual image onto the physical host. This also makes it very easy for our end users to deploy new OSs, because it's literally one workflow that they kick in, and it would go ahead and deploy the latest patches through the new image. This also decreases the turnaround time for us for all the new fixes that we need to push to either cloud or physical infrastructure. And from the management point of view, inventory management, that is, SBOMs would be pretty similar across each of the hosts. That way, it makes it very seamless to account for any of the compliance changes. Since the compliance needs to be run only on the virtual image, it also saves time for running compliance across the board from one host to other where the images are being deployed.
Yeah. So, I guess this is the last part. So, after hearing all of this, if this is the right approach for you, if you answer yes to any of these questions, so for example, if you work in a multi-cloud or hybrid data center environment, do you want to customize your OS images beyond the base one, which is already provided by cloud providers like AWS or GCP? If you want to refresh your fleet of machines very regularly to make sure that you have the latest versions of everything, if you have all the patches, or do you simply just want to meet regulatory requirements for a particular country you're operating in? Then yes, if you do have any of these questions, then yeah, probably an approach like this would be suitable for you. So that would be it. And with that, I don't think we have time for questions, but we will be in the speaker lounge, or the Ask Speaker thing. If you have any questions, so do pop by. And with that, thank you. Arigato.